Good morning. We will be continuing with the discussions that we initiated last time. Uh, now we talked about basic research, applied research. Then we talked about discovery. How important that is. Okay, and then we will and out of that discovery, it's always that some things are not answered yet. Okay, and even if things are answered, they will have to be answered better, in the future, and that is what creates the room for discovery, innovations, etc. And like if you were to look at, in a very very profound way, okay, some of the great unknowns in our and who knows if those will ever be answered. uh, Really, how and when were all the various elements formed? Because everything, what we deal with are all elements. When did these get formed and how? Was it a logical extension of the fusion of hydrogen that we saw, or is it that something else happened? And for that matter, how did life originate on Earth? I mean, it's so profound. And are we alone? Are we the only ones who have this thing called life? And take something as fundamental as chirality. How did chirality happen? How is it that some molecules became chiral? What were the chiral forces which existed? So that these are all very very great unknowns, and you might say that why are we going into so much philosophy? But the point is, some of the future profound discoveries will really come out of answering some of these things, and maybe some extraordinary technologies will come out of this. And now, if you look at in the very recent, I mean, and something which all of you must be reading about and listening to on television, there is, in a way, not too many things which are more profound in their quest than what the James Webb Space Telescope wants to achieve. And it's not as if a telescope was not put in space before. 1990 was the Hubble telescope, which was put 1990. So we are talking about another 30, 31 years later, that this extraordinary telescope has been put in place. Okay. And what does it say? This is the person from NASA, and basically saying what is it that they're looking for. From the very first galaxies after the Big Bang to searching for chemical fingerprints of life, okay, in exoplanets, etc., Webb will be looking at some incredible things in our universe. Now, it's really amazing that at such a fundamental level, people are looking, and I think that one needs to also understand the different levels of creativity, human endeavor, because these are very important. Where exactly do we fit in, into the scheme of things? There are thousands and thousands of people working on a project like this. Not just today; they've been working for the last 30 years, trying to put it up. And again, remember that there are some projects that are so big that no individual can do it, no company can do it. It's not even one country can do it. I mean, over here you have the European agency and the American agency. Both have got together in actually creating this telescope. It's just amazing. And so I think that you may also want to ask yourself that do I want to be part of this kind of a larger project, which could be of great importance, or is it that we want to do inventions at a very individual level? Okay, so and it varies. It varies with the kind of aspirations and mindset you have, your ability to work as part of a team and for a larger cause, and so, I mean, these are classic examples, and within that, each one will have a very, very specific focus. There are thousands and thousands of people working, but each one has got a small. Can you imagine the number of mechanical engineers, for example, who are working on this kind of a project? Fabricating these things. The number of people who are working on all types of sensors which go into all of this equipment. Okay. The kind of software which had to be developed for something like this is just too incredible to imagine. But it's good to have these in front of you because they set a benchmark on what is achievable through human endeavor and where we fit in and where we are with our knowledge presently. Okay. Now, let us therefore now move into inventions, from the area of research and discovery. Okay, and inventions are human-made products, okay, or processes created for the first time. Remember, the qualification is created for the first time. Now, this is very, very strict definition of inventions. If this definition had really been kind of put to use even now, then I'm afraid that there would be very, very few patents, because you cannot, the thousands and thousands of patents that uh, are taking place every year. Many times they are variants of this. They are more, I will say, in that sense, innovations. Okay, so the patents are really on the derivative inventions. Okay, they are also very big. Okay, but if one had to have the strict definition of invention and to say that patents are only given for invention, then the scenario could have been very different. But let's look at some of these. I've just put together, I will say, a relatively more random list. It's not as if there's anything exclusive about this list. I mean, there will be hundreds and hundreds of things that you can write down, as path-breaking inventions. But I just thought that let me take a cross section of a few of these and look at gunpowder, which was first really prepared by the Chinese. And what is it? It's really a mixture of charcoal, sulfur, and potassium nitrate. So these are the fuels, and this is your oxidizing agent. Okay, and now the point is that there is a world of there is a lot of similarity between a reaction and an explosion, as we discussed, when we were talking about immersion explosives. Uh, but there's also a important point of departure that an explosion occurs in such a short time scale, and because you are delivering so much power, so much energy over such a short time scale of a millisecond. So you can imagine the kind of power that is being generated. And it is this power that helps to achieve the kinds of end results, like you can form a tunnel, okay, which is otherwise unimaginable that someone could just form a tunnel in the mountain, and what a profound impact it has. Of course, it can be put to very destructive use also, as we know. But once this concept has been created that I can actually perform something at such a short time scale that it can generate a blast, a huge blast. Okay, and which then allows me to do things which otherwise I could not have done. Now, once you've got that idea, whether after that Nobel took it to organic compounds which could be nitrated, and he ended up making dynamite. Okay, I mean, I'm not saying that it is not important, and it's certainly important, but Nobel's work is clearly an innovation around gunpowder. I mean, the original invention of gunpowder, once you tell somebody or once you show somebody that something like this is possible, then of course, people will start looking all over, and try to see what is possible. And they will come up with products, processes, etc., which are far, far superior. But remember, had that concept not been born, one is not sure whether they would have been able to do it or not. Look at another invention, which is nuclear fission. Uh, Firstly, who would have imagined? I mean, you would have thought that gunpowder is the limit of an explosion, but the nuclear, but even gunpowder, we are talking about chemical energies. Okay, but fission, that you really now started talking about releasing nuclear energies. Okay, and what a remarkable invention. And remember, it's an invention, it's not a discovery. It had to be made, it had to happen. And just like liquefaction of air, of course, air has the potential to be liquefied because it's a real gas. But it had to be made to happen. And unless it happened, nobody would know that it can be liquefied. Uh, and also take something like nitrogen mustard. Now, I would put this under invention because nitrogen mustard had been created as a chemical weapon of mass destruction. It was used by the Germans. The number of people they killed, okay, with mustard gas. Okay. And I mean, it's all, even today, it's used. There are people who are working on chemical weapons, okay, although it's prohibitive, uh, but they've used it. But remarkable as that is, uh, who would have imagined that that same nitrogen mustard could have been used in chemotherapy? Okay. And what a remarkable thing, chemotherapy, and the countless lives that it is saving today. We talked about in vitro fertilization because these actually defy imagination. That till it had been done, I think it would have been impossible to believe that something like this is possible. But then, somebody would have also looked at, the way plants replicate, and would have drawn inspiration from something like that. The telephone, I think, again, I mean, this is another invention, the telephone and the phonograph, that, I mean, people knew that they could talk to each other. I mean, you do it when you are close by, okay? But that if you are miles away, that you can talk to each other. What a remarkable invention! And today, if you are seeing, and we are all in awe of the mobile, but don't forget that the mobile is a derivative invention arising from the original invention of the telephone. Okay, it's incredible in the sense that things which had to be wired, and today you can just be anywhere, traveling anywhere, even flying, and you can speak. What a remarkable thing, phonograph. I again, why I put it is that just like we talked about, you of course, I mean, people can sing, people can listen to someone speak, but who would have thought that you can record things for posterity? I mean, that even if a person is not there, that person's voice lives on. I think you need to take yourself back to those times, yeah, and then you will understand the magic of these inventions. Because I think we are so used to these things that one doesn't quite recognize how profound they are. Or take bakelite. This is the first plastic that held its shape after being heated, and they were actually also looking at it as an ivory substitute. And but look at the kinds of things that bakelite led to. Not to speak of its profound role in things like our plugs and all the things that help you not to get electrocuted and short circuited. Okay, and then the number of plastics that spun out, out of bakelite is amazing. The bakelite, and the second thing which I'll be discussing later on, the quest for transparency. These were the two very, very profound things that led to all of these inventions around plastics. And you have to ask yourself, uh, what are your today's inspirations? What inspires you to invent, to innovate? Take the ruby laser, nothing like this was known, although the lasing action, had been predicted by Einstein. Okay, but to actually prepare something like a stimulated emission, and that in such a with such a level of coherence, you can release light, that for example they showed, I remember in the, I think it was in the 70s, that they actually aimed to lasers at the moon, and from the moon those were the only two things which were visible. I mean, that is the level of coherence of a laser. And today, after that, again, to imagine the kind of applications, whether it is surgery or anything, the power of the laser in communication, who would have imagined? And look at again an invention, pasteurization. uh, well, I mean, milk is known, heat is known, okay, but that if I boil the milk, that it kills all the bugs, and which means that I have to know that there are germs which are lurking in the milk, and the importance of pasteurization, and subsequently to pasteurize so many other things. Or take the case of liquefaction of air. As I said, I mean, it's impossible to believe. I mean, if you go back 120 or 140 years, and if someone said, I can liquefy air, I mean, people didn't even know what air is. There were so many mysteries around air. Air used to be air when it was used to burn something, okay? It used to be called burnt air, and that's what it was called, before the discovery of oxygen. I mean, that's the level of knowledge of air. And where does liquefaction of air fit into all of this? Or, of course, for a long time we knew that, for example, you can take advantage of the wind, and boats can sail, and so those were the earliest modes of transport, sailing boats. I mean, just propelled by the wind. But self-propelled vehicles, which did not actually take the assistance of that kind of a wind, okay, and they were self-propelled. And whether it is propelled so that it can lift off into the sky, or it can on the ground. you know what an amazing thing. Okay, self-propelled vehicles, the ultimate, of course, being the aeroplane. Okay, and so very profound. Okay, and now if you look at innovations, okay, take some innovations for example. Okay, where I have again tried to define innovation as an extension, and let's look at the definition. Innovation happens when someone improves on or makes significant contributions to or diversifies the utility of existing product, process, or service that has already been invented. Okay. So this is the strict definition of an innovation. Okay. And I've tried to, in that spirit, I tried to list out just some innovations. Okay, there could be flaws in my reasoning. That's what I've put it down. Okay, some of them, it's a bit difficult to judge. Okay, but I still thought I'll put it just so that I can. Provoke a kind of a discussion or a question from you. As we said, I mean, after the phonograph had been invented, okay, and people knew that you could record sounds for posterity. Why posterity? Even for now, but you could record and play. Not just record, you could record and play. Okay, I mean, after that, if you take whether it is the Walkman, which probably some of you may not have even heard of, it may have gone obsolete, but it was such a big thing at one time, or the tape recorder, which I mean, very few people use today, or the CD player, all of these things, or now the mobile, all of these things are innovations around the phonograph. So, to that extent, of course, they're very extraordinary, but still, they will not fall into the category of invention. They will fall into the category of innovation as per this definition. As I told you, I mean, this is not the definition that would probably be used in the patent office, and they would look at inventions, no innovation, only inventions, and these would all probably fall into the realm of inventions as per the patent office. But as per the differentiation between invention and innovation, I think that this is quite a good definition. A lot of people also say, hey, forget all this, what it is that innovations are what makes you or helps you to make money. Okay, I mean, so that's the definition. I mean that you can have all of this, okay, but once you start actually making money, and you make money when people start using these things, and so I'll just maybe put it, because this is not something that necessarily is normally put, but maybe it's not a bad way of also differentiating between an invention and an innovation. Okay? Uh, Take again the case of optical fiber. Of course, optical fibers. What an extraordinary finding! That you can make an optical fiber, and basically taking advantage of total internal reflection. We will be covering the patent on optical fiber. Corning's very famous patent. Okay, we'll cover that, and a few other such inventions. Okay, but once the optical fiber had been created, people started looking, where all can I use it? And this, by the way, is something that you can keep doing. Keep looking at, where can I use it, where can I apply it. Okay, and like an endoscope, who it made it so easy to be able to visualize what is happening inside our body. Okay? And or for example, where you're doing all these big reactions in a plant, and you can't take the plant to a UV spectrophotometer or an NMR machine, but the moment the optical fiber had been created, and you could make bundles of these fibers, you could actually put it into your reactor vessels and in real time monitor the progress of the reactions. You know, what a profound impact on chemical process monitoring, which you can simply do because of these optical fibers, and that's optical fiber spectroscopy. Such a big area, and imagine the number of places where you can apply it. In similar light, you can also imagine that many times you have a structure, okay, and you can't move the structure, but I want to see the finer details. Maybe there is some very very small micro cracks which I'm not able to otherwise see, and then the thought that, okay, if I cannot take my building to the microscope, I can put my microscope on the building, and so to make portable and extremely small microscopes, which I can just focus it on the particular part of the building, and be able to see what I want to see, okay? Or any other moving objects. Maybe it would be a pipeline where there's a crack, a micro crack, which I cannot see visually. I have to have a microscope. And just imagine. So, this is another wonderful way of inventing that if you cannot bring that object to me, I will go to the object. Okay, and and you will see this, when we discuss the TRIZ methodology. Okay, take the electric arc furnace. The electric arc furnace, which was invented by Henry Moissan. Okay, maybe I'll send you an article on Henry Moissan, because certainly one of the greatest, and again a Nobel laureate. Very very famous Frenchman. In fact, I was very fortunate. They have a Henry Moissan Prize, international prize, which is given actually not for his work on the electric arc furnace, but for his basic contributions to fluorine. He was the one who first isolated fluorine, and I was fortunate to be on the board, which decided the international prize winner this year, and but an extraordinary man, Henry Moissan. Okay, but once he had made the electric arc furnace, and what was it that he was interested in? He said, I don't want to be constrained by a temperature, of 800 degree or 1000 degree or 1200 degrees, which I can get from an oxyacetylene flame. Okay, I want to go beyond. In fact, forget about oxyacetylene. There was Henry Moissan's thing happened even before the oxyacetylene flame, because oxygen had not even been created at that time, the pure oxygen. Okay? It happened later. But Henry Moissan, after he made the electric arc furnace, and then, the revolution in steel manufacture, in aluminum manufacture, making calcium carbide and opening up the entire area, a whole new branch of organic chemistry, it's just mind boggling. So I would again call all of those things, whether you made, of course, once you have made the electric arc furnace, it's like a technology platform. Then I can use it. I can say, hey, I can make phosphorus out of it. I can make magnesium out of it. I can make steel out of it. Name it. Yeah. But they would all be innovations around the electric arc furnace. Okay. Take Ziegler-Natta catalyst, again an invention which we'll be going through later. And of course the Ziegler-Natta catalyst was a great catalyst, and it really was invented for polyethylene, and later on by Natta for polypropylene. Okay, but the diversification of the Ziegler-Natta catalyst and the number of variants that were created and the number of different types of polymerizations that could be carried out, is absolutely mind-boggling. Okay? Or take chlorine. Once chlorine had been isolated and produced chlorine. I'm not talking about chloride, but chlorine. Okay, and and then people said, "Oh, I can starting from disinfecting water, you know, to chlorinating all kinds of molecules and the number of different chlorinated molecules which were industrial products. Uh, None of those could have happened but for the fact that chlorine had been made, Cl2 had been made. Okay? The same way that after fluorine had been made by Moissan, the number of fluorinated products that could be made. Okay? Uh, there's another, very interesting example that that always fascinates me about innovations. And I think it's a good illustration is the hot air balloon. Okay. Now, of course, I mean, man and woman had this yearning, okay, to fly, okay, and even fly before the aeroplane. Lift yourself up. Okay. That's such a natural instinct, and when you look at a bird flying, and you can say, Why can't I do it? Why can't I be up in the air?" Okay? And so it was that kind of a yearning. Okay? And in fact, I told you about uh, the the aeroplane which flew only on solar energy, okay, with not a gram of any fuel. But really, one of the people who was the pilot of that plane, his grandfather actually was the person who first went to the stratosphere in a balloon. And what an amazing thing! And he was narrating it to us, about his father and going to the stratosphere. You know. And but in terms of the specifics of the balloon, okay, I think it's very very instructive that what's the first thing that you need to do if you want to be in a balloon? What must it have? A balloon?
Carrier type of thing, and a basket.
Say that again.
The hot air balloon has a basket, so it should have a carrier
Yeah,
kind of.
carrier. But then I don't sink, right?
Yes,
So what must it fundamentally have?
a gas that is lighter than air. Like,
Absolutely. So what you're now talking about is that I have to be made lighter than air. Otherwise, how will I go up? I can't. And so what was the first thing that people might have thought of doing, or what did they do? Do you think?
Used air itself.
Air itself. But if you have air, okay, and if you are you make a balloon with air, and you are also there, and it has to carry your weight, then how I will go up?
You can heat the air. Maybe
Right. Now, wait, this is very interesting. Okay. You are now talking about the hot air balloon, right? And
yes.
what a brilliant invention that the I can reduce the density of something by heating it and lower its density. And so, I just become lighter. The air itself becomes lighter. But the remarkable thing is that today, see, this is the other thing, because we are so conditioned seeing what you're seeing, that if you think that that was the first invention that people had is not true. You know, people actually knew how to do electrolysis of water. After electricity had been created and the battery had been created, so they could make hydrogen. And once and people figured out that hydrogen is lighter than air. Okay? So the first balloons which were made were hydrogen balloons, and just taking advantage of the lightness of hydrogen. And later on, people realized there must have been situations where the hydrogen caught fire, because after all, it's going, and you've got air all around, there's oxygen. Okay, all I need is a spark, maybe a lightning, and it might catch fire. Okay? And so people could not. People had to invent something better, than hydrogen. So what would be the next best thing that you might do if you knew that?
Helium we can use.
Wonderful, wonderful. That's precisely what people did. They and by that time, helium had been made, and they said that helium is also a very very light gas, much lighter than air, and helium is inert gas. They figured that out. That unlike hydrogen, you can't ignite helium. And so the next one was the helium balloon. Yeah. And but then people said, helium is very costly, and you cannot make it a very popular thing with helium. And so again, that thinking had set in, that can I replace helium? I've overcome, of course, the problem of flammability. Okay, but can I replace helium? And that's when someone had this brilliant idea that the heated up air itself is lighter than air, and came the hot air balloon, which is now what people use. What you can also see is that these kinds of great innovations were sparked by basically identifying limitations. There are some people who always will try to find uh, some limitation or some flaw with what exists. Now, one thing I always keep thinking is that if there is one thing which is there all around us, okay, it's nature. you know. And the number of ideas that you can get from nature, okay, is absolutely mind-boggling. Whether it is to have seen the bird fly, and you want to fly, okay, which is only one example, uh, to so many things where you can draw an inspiration. And I was just thinking, it so happened that at that time I was in the Technology Council of Asian Paints, and and so my mind was always going in the direction of paint, at that time. And uh, they had made this kind of uh, wall coatings, which became quite popular. These are the textured coatings. Now, till that time, the concept of paint was really different colors. Okay, so you chose your color, okay, yellow, white, blue, whatever you want to, what fascinates you, okay, and you put it on the wall. But walls, even today, the majority of walls are basically very smoothly painted, okay? And with a color, and what you're really appreciating is that color, okay, on the wall, and the smoothness of your coating. Okay? And then how can I create non-uniformity within uniformity? Right? So I say that no, I don't want 10 different colors. I just want one color. but I still want to create something interesting, okay, an effect, okay? Because paints are all about effect all the time. In your room, you seeing your wall and you marvel at the wall, or you can hate it, whatever. And someone actually then made this thing. I must tell you that the first time when I saw textured paint, I thought it's so beautiful, yeah, that you can create this kind of an effect. Okay? By the way, that reminds me, how would I create that kind of an effect?
Sir, like we use different kind of brush or something like that. The roller was differently shaped.
Very, very nice. Excellent. Excellent. Yeah. Uh, and is that the only thing that you need to be worried about?
So the paint thickness also, like if we are trying
Brilliant,
to make a
brilliant, brilliant.
pattern.
Very good. Okay. It requires both. Okay. In other words, obviously I need some kind of control of rheology. If something it doesn't have any kind of lag, and the moment I sort of withdraw the shear, that it will relax and become absolutely flat, then of course it's not going to work, but if there is a finite time, okay, within which there is some kind of curing of the paint that happens before it can level out smoothly, okay, then my creating this kind of a non-uniformity with a brush, okay, will lead to a permanent kind of fixing, okay, because I have been able to control the relative rates of curing and smoothening. Okay, and then you can go into all the knowledge and the science that you have learned of how do these things get controlled. What do I have to do? Okay. And so I hope you can see the linkage between very, very profound fundamental research, and this kind of an effect. you know. But I was, I couldn't help but think. I remember, where did I go? I'd gone to some beach and I took this photograph, and I was just thinking, look, I mean, I could have got this inspiration for say something like this just from the beach. Have you seen the beach in some places? You know, and it creates an amazing pattern. And I thought that there is some roughness in that sand. Then I went and felt it. I said, no, it's quite smooth, and yet you're left with this remarkable effects. Of course, it is coming from uneven wetness, of the sand. Sometimes these effects are created. Sometimes the effects are created because of genuine, sort of non-uniformity in which you can actually feel with your hand, with your fingers. Okay, but in other cases, it's quite smooth. But what I'm trying to say is that you know I'm sure that people who thought of textured paints, somebody would have actually seen these kinds of effects in nature and actually found them quite interesting. And non-uniformity created out of uniform systems. It's all sad. And so again, I'm just saying this could be a very different inspiration, not the same kind as seeing a bird fly. But nonetheless, I drew my inspiration from nature. Or take this case. You see these beautiful mosaic structures in tiles. Granites. There are so many granites you can cut and you can when it's polished. It looks so lovely, and people put them in their kitchen or floors and all kinds of things, right? These kinds of structures. And what appeals to you? What appeals to you is that now we're not talking about a uniform one color, but you're actually talking about at least two or three, different kinds of particles that I'm able to see. Okay, I'm seeing some black spots. I'm seeing some pinkish, all of this stuff, and this creates also a beautiful effect. Now you say, yeah, I mean, I've got this, okay, and I want to make this. I want to make a coating in my wall, okay, which looks like this, okay, and you can see that people have tried to make these kinds of non-uniform structures. Yeah, you can see it better, right? You obviously may not be as pretty as this, but nonetheless, people did try and make it. Now, let's say you gave this great idea of a brush, which will achieve this. How would I achieve this? What would help me to achieve something like this as a coating?
And sir, maybe addition of different colors while
Yeah.
painting.
Now,
So we'll add.
and different colors. Yeah, you mix different pigments, right? That's what you're
Yes,
trying to say. You
yes,
what do you think are the dimensions of these things? You can see them with your eye, right?
yes,
Isn't it? I can
yes,
see these things with my eye. Now, if I have got, uh, so obviously, the size is what? If not a millimeter, maybe certainly within zero point 0.1 millimeter, right? Okay, that kind of a size it would be, isn't it? Huh?
yes, sir.
So maybe 0.1 to 1 millimeter, and some of them could be even bigger. Okay? And the problem is that when I put pigments like that, okay, in a let's say an emulsion paint, okay, those pigments would be so heavy, and so big, okay, that there will be a natural tendency to settle down. Okay, it will be very difficult to keep them dispersed, okay, under those conditions. So I you agree, isn't it? I mean,
Yes,
many of
yes,
these things settle down, right, if they're too big.
yes.
Right. So what do I need to do to still get this, but also keep my paint stable?
Sir,
Yeah,
can we like use emulsions
yeah.
that become unstable when exposed to air? Certain, say, a droplet size or something. So when we apply, some parts of it will break up. Like when it is in the paint box, it is like small bubbles, not bubbles but droplets.
Yeah.
And when we apply them, when
No, no,
exposed
the
to air,
emulsion paint is already a emulsion, isn't it?
yes,
Huh?
but that droplets when exposed to air will become unstable. So when they burst, they will leave patterns. Like burst or just go away. So
That's a very interesting idea. You I think quite good. All the suggestions that you all are making are excellent. I want you to shed your inhibition. If you think it's a good thing, that's it. You be your judge. There's nothing wrong. At most, if 20 ideas come out, I have a way of screening those ideas and maybe identifying two or three out of those. But what's wrong with it? Okay. And I remember one of the very early brainstorming meetings I participated in Australia. There was something called a Global Research Alliance among many countries, and I was on the member from India in the area of water. And so we were having our brainstorming meeting, and I'm talking about what, going back to 2001 or thereabouts, and we started rattling off thousands of ideas on what we should do in water. And I remember at that time, not exactly using the word water footprint, but effectively saying the same thing. Okay? And the moment I said it, not as elegantly, okay, another guy immediately then said, "Oh, so what we are talking about is a water footprint." Of course, people had been talking about carbon footprint, but there was no talk about water footprint at the time. Today, water footprint is a very big thing. And so what I'm saying is, don't be inhibited, please. And you'll find that always your brilliance will be reinforced by somebody else, who will come up with a still better idea, just like the hydrogen to helium to hot air. Okay. So what you said is, one of you said mix different pigments, and I'll put, but you also saw difficulty, right? Is that correct?
Yes, sir.
Then you said make immersion droplets burst. It's a good idea. Make immersion droplets burst to create unevenness, right?
Yes, sir.
Okay. Any other suggestions from anyone?
Sir, we can use like emulsion within an emulsion also.
Wonderful. Believe it or not, that's one of the
Water
ways
in
in which
oil or
it's
something.
done. Very, very nice. Okay. In other words, you're talking about multiple emulsions, right?
Yes, sir.
Okay, water, oil, water type of emulsion, or oil, water, oil, and you can make multiple emulsions. Okay, very, very nice ideas, and in fact, uh, you can broadly, okay, see, that's where uh, detailed knowledge comes in. Like each one of you will have great domain expertise, like some of you in the area of chemical engineering and all the things that some of you in the area of, let's say, oils and polymers, someone in the area of surfactants, okay, and you'll have all this kind of, or textiles, and you can have such brilliant domain knowledge, but best thing is that when you're looking for a solution, one is that be like me, who knows very little of anything, So that's the best thing to do. Okay, you shouldn't know too much, yeah? Which is my big advantage. I really don't know too many things in great detail. Okay, and but uh, you can say, okay, if something which is big will not it's not possible to suspend it and keep it suspended, but is it possible that I can create a situation where under some conditions very small things can start aggregating to become a larger thing, and all that will happen between the time of applying the paint, okay, to it actually curing up. And so, you can broadly say, if big cannot be kept big, okay, make small things big. Oh. And or you say something in your own way, okay, and so those kinds of things are the way you should look at solutions. Do not look at the detailed solution right away. Always look
Sir,
for broad general approaches.
sir, we can also like do the other way around. We can have bigger things and then make them break down when we are
That's
up.
also very smart. Okay. Uh, Small thing. No, no, but bigger things means how the bigger thing will be stable.
So like each individual color will be there, and then somehow they break into tiny
No, no,
droplets
but
in each
no,
other.
no, but the color would be what? It would be a particle.
That I don't know.
If it is particulate, then if it is bigger, then it will settle down.
Yes.
You understood, no? So the you know the reverse may not be viable. By the way, this is also very interesting. You also be your own biggest uh, uh, critic. You know, don't wait for others to criticize you. You be your own critic. You propose things, and you reason with yourself whether you think it's a good idea or not. Many times, you will come up with an idea and you will shoot it down yourself. You don't have to wait for somebody else to shoot it down. Understood? All clear to everyone?
Yes, sir.
Okay,
Yes.
but I'll put it down. Uh, Small things that become big. Okay. Uh, uh, I'll just say converse, maybe as suggested, may be difficult. Okay. Agree? Agree with all this?
Yes,
The
sir.
general approach, uh, an idea that came to me, I'll just put it down. Liquid crystals. I have no idea. But liquid crystals also have this. Uh, uh, you can actually make them aggregate. And they sometimes produce great colors. There are all kinds of liquid crystals. You can read up about liquid crystals. Uh, but that would be also something I thought maybe it would be of interest. Okay. Now, one thing, another thing that came to me just now, so I'll put it down. This is something that Dr. Mashilkar would occasionally say during some of his lectures, which I always found quite interesting. What he would say is, we have talked about innovations, but we haven't talked about the innovator. Because that's what the innovator has to make the innovations, right? And many times naivety, of course, helps in the innovation process. And what you would say is an innovator is one who does not know that it cannot be done. Okay, because if you are too knowledgeable, this that you'll be of course very knowledgeable, but you may not innovate. Okay, and many of these people, they just say, I want to do it. They don't know that it cannot be done, and in the process, they figure out how it can be done. I'll just put it over here. Uh, Quote from Dr. Mashilkar. Okay. Now, while I was looking at all this, and I must also tell you that one of the things which is quite interesting to look at is again drawing inspiration from nature, and you look at the kinds of beautiful colors and patterns that are created by nature. Take the peacock's feather, just so amazing. Okay? And you go and actually take apart a feather, okay? You'll find it the most boring thing. You don't see these kinds of or take mother of pearl. Look at these things. Yeah. Look at this. So beautiful. Now, what happened was that you know our concept of color is by and large uh, being derived from this very chromophoric view of colors. That color is because of a chromophore. You uh, but you can actually generate colors from interference effects. There are all of these are interference effects. Okay, and believe it or not, uh, it was Newton was one, and the other was Hooke. The Hooke's law of fame. Okay, Hooke, Robert Hooke. He is the one who actually started conceptualizing, these kinds of understanding colors which are formed because of interference effects. Okay? And so maybe that would be another very, very interesting way of generating some of those patterns and colors that we are talking about. And let me tell you, if you also look at in making chromophoric colors like these dyes and things like that, the amount of uh, uh, waste that is generated, in terms of chemical process waste. Okay, I might be able to actually come up with these very clever ideas because, after all, it is I'm really looking at the top surface. So they are more like surface effects, which I need to worry about. I don't have to really look at what's happening in the bulk of the structure. So how can I manipulate structures on the surface to create this kind of effect, which one can call it as iridescence, where it also where really the color is changing depending on the angle at which you are viewing. That's also very interesting. That it depends on the angle. This is one of the first cars which was made based on this kind of a concept. You can see it's a car which was painted with iridescence. Okay? And it's quite interesting. You may not like it. I don't know whether you like it or not. Okay, but you can see. I mean that it's got different iridescence. Okay? So I would say that, or over here, actually, you find that many biominerals, the way they aggregate, okay, their structures, okay, leads to this kind of iridescence. Huge amount of very sophisticated work has been done around the mother of pearl. Probably the most sophisticated spectroscopic techniques have been brought to bear on studying these kinds of things. Okay? In fact, I remember I used to be the head of strategic research in a part of ICI in England. That was one of the biggest centers for colors research. I remember, asking them and talking to them that why don't you open a branch which will only focus on these kinds of colors? Just to tell you that you can actually think in a very different way. Okay, I prepared these slides yesterday. Okay, and again, I was just thinking about drawing inspiration from nature. Uh, and I remember there was maybe about 15 years ago or around that time, I was having a very nice chat with some people in the defense laboratory in Jodhpur. Okay? Oh, the reason was because at that time we had invented the world's first animal-powered reverse osmosis unit. Although we kind of ran it with oxen, there was a person he was the chief secretary to the chief minister in Rajasthan. He said, Dr. Ghosh, I'll try and run it with camels because in Rajasthan we have camels. And so that was running on camels. One camel would go round and round and desalinate water. Okay? So that was very interesting. And it so happened that because of that, these people in the defense laboratory in Jodhpur got in touch with me because they work on camel research, and they also work on defense. Okay, and one of the problems, he was mentioning to me, is that troop movement across a desert. And when you have got these sand dune, you know how difficult it is to walk on sand. Okay? And, and what they did was something remarkable. I learned from them. They actually studied the feet of the camel, okay? And wanted to know how is it that camels are able to walk so nicely on sand. Okay? And they ended up actually creating a special shoe for the our soldiers, which actually drew inspiration from the feet of camels, and which allows you to walk more efficiently on sand. And so it's not as if they basically copied nature. They copied the foot of uh, the camel, in doing this. There's no end to this, and you look at these lizards. Okay, they're able to basically just from the ceiling. You see the way they hang; they don't fall down. And so how their stuff is helping them to cling on, to this ceiling. How are they doing it? Yeah. And in fact, there's been a lot of work, and it's like actually what you find is that they have things like suction pads. It's almost like a suction pad. You know that with suction pads you can actually stick things, okay, on walls and stuff. And so nature has made things for them in this manner. Okay? Or you see the monkeys climbing up the tree, and look at this contraption, which helps you to climb up these tall trees. Okay? I mean, otherwise, it's such a problem when you have to pluck out those coconuts and things like that. Okay, and nowadays, because of labor shortage, earlier you had people who would do this, but today it's much harder to do. Okay, and it's not so easy to find people who will climb up these trees, and so many times, all our fruits and all tend to rot simply because you can't get people to climb up and pick these things. And then this beautiful device has been made. Okay, you might want to go and find out about this device, which actually helps you to climb up these trees quite nicely. Okay? So it would be wonderful, right? Having something like this and being able to climb up. And of course, you never know. Later on, people might say, why don't I just go up in a hot air balloon, okay, and then go and start cutting these fruits from the palm trees, or someone might say, why not a drone to do the job? Maybe you could actually then think of many ways of solving this problem. Okay? And not only that, literally like monkeys, these guys can actually jump from one tree to the other. They don't climb down and then go to the next tree. And so, I mean, there are things, obviously, you will draw inspiration from monkeys and things like that, how they climb up and jump and things like that, and see if you can do something similar. Yeah. Uh, Now, this is the world's tallest tree. Okay, these are the California redwoods. Okay, and these trees are they can be even higher than taller than 300 feet. And if you look at, okay, that what allows all these nutrients and water and all to climb up 300 feet, how does it happen? And in fact, there's a very famous person called Pfeffer who Van Top mentions in his Nobel lecture. And Pfeffer was actually trying to understand these things. Okay? That what's the mode of transport? You might say capillary action, you know, but capillary action over 300 feet, that would be phenomenal. Okay? But clearly, the nutrients, etc., are reaching here, okay? And they must have been reaching from the soil. So, what do you think might happen? How do these things work? See,
So
yeah,
maybe there is some kind of suction that is created from the leaves because they are
very
respirating.
interesting. Very interesting. Uh, some kind of very interesting. Create uh, leaves create, right? You're saying leaves create uh, some kind of suction effect, right?
Yes, sir.
That's what you're saying. So it would be like a vacuum. Hmm?
Yes.
Anything else? Yeah, and you know that of course you're talking about 1 bar is equivalent to about 32 feet of height. So 300 feet you're talking about 10 bar in the opposite direction. So the kind of vacuum that you need to create, you'll get some idea, okay, of what you need to create. Any other way in which you might think of how that might happen? Anything? So, I was just thinking, I'm not 100% sure whether this is correct or not, but maybe Pfeffer was actually trying to say something similar. Uh, See, what happens from the top when the sun is shining? What happens here? One is, of course, you have photosynthesis, right?
Yes.
What
Also,
else?
water gets evaporated.
Absolutely. Water gets evaporated from the top because of transpiration. Now, when water gets evaporated, um, what can happen?
Yeah.
Huh?
So voids can be created because now there is
Void.
nothing.
Voids तो ठीक है, but how voids are not going to help you to lift the thing up.
So like osmosis only, the
Oh,
water will move.
wonderful! Yeah, osmosis only. So what happens?
The water from the roots will move up where it is less, where it is lesser important.
Absolutely. Okay. So, in other words, see, if there are certain nutrients, etc., or some solids or salts, which are there, as it is evaporating, so what will happen is that my salts will get more concentrated, okay, and therefore I will have a higher osmotic pressure, right, created, because osmotic pressure depends on the concentration, correct?
Yes, sir.
Yes. So, what will happen is that this continuous evaporation of water and the creation of maybe more concentrated solutions, okay, might actually create the osmotic pressure gradient between the top and the bottom. Okay, creation of osmotic pressure gradient. Like, just to give you an idea, okay, we did a calculation of the osmotic pressure of just saturated sodium chloride solution. Right, and this is also known in the literature. I mean, but you can actually calculate it. Guess what is the osmotic pressure? For that matter, what is the osmotic pressure of seawater? Do you know? Of course, you can calculate it out. You know, even seawater, you can calculate from pi is equal to CRT, okay? And you know the concentration of sodium chloride. I mean, you can approximate it as a sodium chloride solution, 3.5%, and you know that it will dissociate to two ions. Okay, so I'll write pi is equal to 2 times CRT, which is my sodium chloride concentration, 3.5, and I'll convert that into moles per liter. Okay, and then I can work it out. Okay, and the osmotic pressure at room temperature comes out to be about 26 bar. And so if you see that 1 bar is equal to about 32 feet of water, then it's not so hard, right? Creating the osmotic pressure gradient between the top and the bottom. Okay? And if it gets still more concentrated, then of course you can go to taller trees. Okay? So what I'm saying is, it's always ask these questions, okay? Because the greatest of scientists like Pfeffer asked or went off, they asked these questions. And so if you have that childlike curiosity to ask questions, okay, then you will actually find fantastic work to do. And so it will not just be questions for making always a product or a process. It could be just a question which will help you to then derive some equations, maybe new equations, conduct simulations. You can do whatever you want, whatever suits your fancy, okay, or whatever you're skillful at. Okay. But most of us are being trained to solve problems, okay, uh, and solutions are emphasized, but not so much the what kind of problems to solve. And that's a problem. I mean, people, if you tell them solve this problem, they'll go in no time and solve the problem. But could they have thought of the problem themselves? Not really. Okay, so do not, I think this overemphasis on solutions, and underemphasis on conceptualizing worthy problems to solve. After all, this would be a great problem to solve. Okay. And even if Pfeffer and Vantoff had worked 100 years back, with all the sophistication at our disposal today, I mean, can you come up with more quantitative solutions? And who knows? Maybe if somebody will go and look at the top of that tree and analyze and see what are the fluids and what is their osmotic pressure. I just have to do an activity measurement. Maybe I can go in a hot air balloon, to the top and pull up something from there and analyze it, right? And do it. If possible. All right. So I hope you can see again how you can creation of osmotic pressure gradient, which may help to pull things up from the soil. All right. Now, yesterday I was also preparing just out of fun. Okay? I was preparing this slide, and I was just trying to see, it may not be always nature, okay, but it could be nature. But you see something so interesting sometimes. When I was looking at, let's say you see this toothpaste, right? And you see, these stripes over there. It's so interesting. I mean, I was just wondering, how are these stripes created in the toothpaste? Anyone? I have to go and read up. I don't know the answer. But how are these stripes likely created?
So there are 3 to 4 nozzles that are pouring the toothpaste simultaneously in the tube. So each nozzle pours a different color of toothpaste. So that's
Right, and then, but again, what you have to look at, it's almost like doing an extrusion, but you'll have to again make sure that you have controlled the rheology, right?
yes, right, right.
Because you see, if the rheology is not right, you need sufficient kind of mixing at the boundary that it all becomes one coherent thing, right? Otherwise, there will be strips and they will fall off. But at the same time, they should not be so fluid that the color just disperses. Okay, you can imagine the amount of work that must be going into controlling the rheology of something like this. It's just fascinating. Yeah. Uh, you know, I was also, and this used to fascinate me a lot when I was a kid. So I just thought that I'll ask you. See, this is of course these very tasty rasgullas, but there used to be one rasgulla that we used to get in Calcutta, and I'm not sure. Well, yeah, I think they're still available. We used to call them Rajbhog, but I know that Rajbhog is a different sweet in different states. Okay, but this Rajbhog was very interesting because uh, in the whole, in the inside, right in the inside, when you cut it up, okay, there is it's like a cavity, and so there's a hole over there, and of course this is all around the rest of it, but the inside was that cavity. So how do you think they created the cavity?
Don't know, sir.
Yeah, yeah. Actually, I mean, neither did I. It was some person who had worked in these mithai shops who later on told me, what they do is that they actually put a big crystal of sugar, in the middle, and then they put the paneer, this stuff, around that. Okay, when they make the ball, right? And then when they boil that stuff in the syrup, that crystal dissolves. Okay, and by the time the other stuff has kind of given you the green strength, it doesn't collapse in the middle. Okay, and so it leaves a void inside. So the void is really created by a sugar crystal. Quite interesting, I mean, when I came to know it, it sounded so fascinating. Let's put it the other way around. I used to be very fascinated, and then when I came to know how simple it is, the way they do it, I mean, you feel a bit stupid that why you never thought about it. But I mean, that's the thing about innovation. Once someone tells you the solution, it all looks so easy. But till that time, nothing is easy, let me tell you. It's no different than from any time I used to go and see this PC Sarkar magic shows or these card tricks, that people play. I could never figure out any time what they're doing. And it was only, I remember one friend of mine, he was a very famous scientist, Dr. Sumit Bhaduri, and Sumit was not only a brilliant scientist, he was a great magician, And so one day he told me that, Pushpita, would you like to be my assistant for one magic show? He was doing a magic show in Vashi, I think around 1985 or 86. And So I was backstage, helping him as he requires his things. And some of the things I said, that's it. So stupid this thing is. It's so idiotic. But the effect for the audience is so mind-boggling. And and it's all part of innovation. I mean, if you don't know it, it sounds so difficult to figure out what's going on. And this is again, borrowing on from the Rasgulla. You look at these bones, right? And they're hollowed. Okay? Um, and some of them have marrow, I mean bone marrow. Okay? And again, I mean, it's amazing, fascinating. How exactly do you create this hard structure which is also hollow? And all of these must be based on templating. Okay? So I have some structure which is created. Okay, over that maybe I'm actually growing calcium phosphate crystals, because bones are primarily these kinds of calcium phosphate type of apatite type of structures. And so I'm creating those. Okay, and then their micro aggregate would be like those bio minerals. And then after that, maybe the inside is kind of gets cleaned out, or that's where you form your marrow, and that's how these hollow structures get created. And by the way, for this has always been important to us. For example, I'm just showing the cross section of a hollow fiber membrane. Okay? This is one membrane. The dimension would be about maybe about what maybe around zero point 0.2 millimeter, or that kind of thickness. It can vary from zero point 0.2 to 1 millimeter. And and this is your polymer with all the pores, and this is the hollow inside. So for example, we talked about osmosis. So if, for example, if this is your cell wall, and you have got liquid over here, which is very concentrated, from the evapotranspiration process, from your outside, you could have the water, etc., from the soil coming in, getting sucked in. Okay, and it would be basically because of a osmotic gradient that is created across the cell wall, or it could be a synthetic polymer in this case. Okay. Now, the way these hollow fiber membranes are synthetically made is also extremely fascinating. Maybe at some point I'll tell you how that's done. But I was actually, in fact, just yesterday I got back some of the hollow fiber membranes. I sent it to Bhavnagar for doing a coating, and we're going to study it. We're doing some work on making these things in the country. Okay? And so what you have is, I'm just showing you one fiber, but actually you could have thousands of these fibers inside a cylinder. Okay, so they're all stuffed in. Okay? Thousands of these fibers. Okay? And I was just thinking that I mean, it's just a thought that came to my mind. Okay, I was just thinking that you look at this bundle, this hair, okay? uh, uh, nice long hair, and how many, there are thousands and thousands of these hair fibers together, right, in this thing. And if there is a way to discreetly coat each of these with a polymer, you know, and if somehow then I can get rid of the inside part, the hair part, by dissolving it out, in some acid or something where my polymer stays stable, maybe we can have a natural way of making these fibers in bundles, and then just put them into a cylinder, and look at it. But then, if you start looking at the engineering aspects, there are so many issues. If there is even one defect, then you have had it. It will not work. These membranes. Okay, it has to be absolutely defect free. So take this as a challenge. I was just having fun yesterday, just imagining and conceiving these. But actually, it was not just imagining from in a vacuum. I'd asked one of my PhD students. I said, what fascinates me about this hair. At that time, we didn't work on hair. We were working on coir, which is the coconut fibers. And I said, I like what I like about these fibers is that they're so flexible, and they always reminded me of a wire, and they're quite strong also. And so I asked him that can you see if you can coat these fibers with a conducting substance, okay, and then it will be like a wire. Okay? The outside will be metallic. Of course, it will be surface conductivity, not bulk conductivity, and then he was able to do a sputter coating of gold, of course not practical, on this, and you can see, these are our fibers, and you can see the gold coating, it's become like gold on the stuff. These are, yeah, you can see over here. These are this, and we then actually did electrochemistry, okay, with these things, using them as electrodes, and could get beautiful electrochemical response. And basically, this idea yesterday, I thought that while we are doing this coating, this sputter coating, but none of this is practical. But if I can actually use the concept of what concept are we using? Like, for example, while the hair is attached to your head, I can actually tie it up, right, at one end before I cut it. So after that, I cut it. So now all of this is all together. I don't have to again reassemble. It's already assembled for me. So now I just need to take this stuff, and do a spray coating. Okay, this is all ready-made, available. And you look at the number of billions of people, and so many people with long hair, and frequently they will cut their hair, and so this is all available stuff. So it'll be very, very interesting to look at. Another example of templating, when I was teaching you all, maybe not all of you, but some of you, in your industrial engineering chemistry, you would have seen how salt is made, and we talked about how you evaporate seawater, and first thing to come out will be gypsum, because the solubility product of gypsum is less. So in our salt pans, we used to have huge amounts of gypsum, okay, which come out. And what were people doing? They would buy it from us at 1 rupee a kg, means 1,000 rupees a ton. I used to feel so disgusted, and they would just take it to the factory and crush it up and use it in cement manufacture or some other stuff. And once when I went to this farm, I found that there are some pieces, of this gypsum which are so aesthetically beautiful, the way they have crystallized. Solid blocks of things with, you can imagine it's a shape of a face, or an animal. I remember Professor Siana Rao, who is our only Bharat Ratna scientist, and who happened to be my teacher in IIT Kanpur. He had come visiting, and invited him to give a lecture. And he came and I took him and he said, Pushpita, please give me one of these pieces for my museum. He's made a science museum in Bangalore. And so I carried it, a beautiful piece. And I said, why each one of these pieces will be worth 1,000 rupees, and that's how you can create opportunities for things. We just have to look at it in a different way. Okay, like I can look at a hair as a hair, but I can also look at it as a source of hollow fiber bundle, and then it gets so interesting. I can look at the salt works as a place where we can make beautiful gypsum objects, which you can sell. Maybe you can put it in a create a website and sell these things. Okay, but then one of my colleagues, Dr. Mohandas, what he did was, after we got fascinated with these gypsum and all, and I used to always marvel at this thing. He went and he had a clever idea. He went and started making a small metal framework, like a template. Okay, and then he just left it in the salt pan. Okay, and as the seawater was evaporating and the gypsum was crystallizing out, and it used to crystallize on the object. Okay, and look, it's such a beautiful thing. He made a hand. Okay, and it's all gypsum, over here, and so innovative. Okay, and the interesting thing is because our salt works are what it can be 100 feet by 50 feet. So if it's possible even to make giant objects, if somebody were to be interested. Anyway, I hope you can see that how you can draw inspiration from nature, and out from nature you can start going into more these kinds of objects, human made objects. Okay, and the sky is the limit in what all you can do.